Welcome to this computational physics masterclass on simulating chaos using the double pendulum. We will bridge nonlinear ordinary differential equations with Python, SciPy, and Matplotlib. A double pendulum is a simple system of two pendulums attached end-to-end. The equations of motion are a system of coupled nonlinear ordinary differential equations, which you see here. While a single pendulum is analytically solvable, the double pendulum is wildly chaotic. The equations are nonlinear and coupled, making closed-form solutions largely impossible. We need computers to solve this. Our goal is to translate this complex physical system into a five-step computational objective. This includes defining equations of motion, setting initial conditions, simulating the motion, plotting the angles, and animating the results. Stage 1 involves setting up the physical model. Our assumptions are no damping, no friction, and a fixed pivot. We use two angles, θ1 and θ2, and their velocities, as coordinates to locate the rods. To solve this with an ODE solver, we need a first-order system. The state vector, called y, consists of the four components, the angle and angular velocity for each rod. The first step in implementing the equations function is unpacking the state vector y to access the angular positions and velocities. This maps the derivatives of the angles to the angular velocities. The equations function acts as the engine room. It takes the current time t and state vector y as input, computes the slopes or derivatives at that exact instant, and outputs the time derivatives of all four state variables. The last two derivatives are the accelerations, which are nonlinear and coupled. The complex terms show that each pendulum continuously affects the other, which is what breeds the chaos. To handle the algebraic complexity, we define intermediate variables, such as delta, and denominator terms. This makes the Python code cleaner and more readable for calculating the final derivatives. Stage 2 is setting the scene by defining initial conditions and the time frame for the simulation. We start with the pendulums released from rest at 90 degrees and simulate for 20 seconds. The numerical solver, solve_IVP, iteratively steps forward. It estimates the slopes from the equations function, updates the current state, and repeats this thousands of times to compute the full trajectory. The solver returns an output matrix where each row represents a state variable over all time steps. We extract the angular position data by slicing row first to get clean time series arrays. The scipy.integrate.solve_IVP function automatically handles the intense numerical integration using the equations function, the time span, and initial conditions, returning a complete history of the pendulum's angles over time. Stage 3 is plotting the divergence. As seen in the graph, the initial symmetry is broken and the two pendulums separate. The second rod eventually goes rogue, climbing above 5 radians, indicating full rotations instead of just swinging. Stage 4 focuses on converting the abstract angles into Cartesian coordinates for animation. We use standard trigonometry to determine the x and y positions of both bob 1 and bob 2. These graphs are the fingerprints of chaos. The trajectory never perfectly repeats, and the phase portrait, showing velocity versus angle, demonstrates intense sensitivity and coupled energy exchanges. To animate the motion, we use the func animation loop. It iterates through all 2,000 computed frames, with a 20 millisecond delay between each frame, providing a fluid 50 frames per second visual playback. The animation is created by drawing a simple 3-point polyline from the pivot to bob 1, and then to bob 2 for every frame I. The static numerical math transforms into a visceral physical animation. By structuring physical laws into programmatic state vectors, libraries like SciPy and Matplotlib allow us to simulate, visualize, and understand chaotic systems that are impossible to solve analytically.